This video will describe raster basics, as well as a general approach towards spatial analysis using the Spatial Analysis Extension package and employing the conceptual model to conduct spatial analysis. Well, everybody, welcome to the world of raster. And you're familiar with feature data set analysis, points, lines, and polygons, and all the advantages that come with it. Well, by the way, it's a double-edged sword when it comes to feature data analysis. It has its weaknesses too. Well, raster does also. But you're going to see that converting your data into the raster model, it's going to provide a very, very unique series of approaches towards spatial analysis that you wouldn't be able to have done leaving it in its original format. So you have a series of cells that are interconnected to each other, obviously, and you're going to see that the cells have values that are associated with each one of them, and a lot of times those values can be represented using colors. So that in general is what you see there, and you see of course also at the bottom the symbolization of cell size, and you've got a cell there. That's going to play an important role when it comes to talking about resolution. But what can you actually put into raster format? Well, you see a couple of examples that have been identified: the temperature, elevation, spectral value. But it's, well, you can put it into an attribute table. Pretty much you can put it into a grid, even though the system has a way of sort of converting everything into numbers, even things you type in that are text format. So that's just sort of another story. The big disadvantage of raster is this, is that with featured data in the attribute table, you could put a bunch of stuff in there to describe that object. And really, you're pretty limited when it comes to raster. You've got that one value that you're going to be loading up, and so that's sort of the negative side, one of the negative sides of using raster. So now, what happens when you take feature data and you convert it into raster format? Well, in this example right here, you see several polygons. You say goodbye to that nice crispness that you're used to seeing in the feature model, and suddenly you've got the world of teeny tiny boxes that are connected to each other. And well, it looks like you've already, it seems like you're on the losing side of things. They say, hey, look at those lines, they're not smooth anymore. I see all these little blocky cells, and that's bad. Remember again that raster has its strengths over feature data when it comes to certain types of analysis. But also, there's this belief in the industry that, okay, if it's feature data, like to the left, okay, now it's got to be, just better. That's not so. I've seen studies where I've seen people be very, very meticulous when it came to creating raster data, and I've seen people who create absolutely crummy stuff when it comes to feature. And of the two, I would most definitely trust the raster over the feature. So it just depends, everybody. It just depends. But still, you're seeing though that there is this general conversion that's going to take place when it comes to the shapes of the feature data. So now, what is one of the major qualities of raster data that helps determine whether or not, well, I hate to use the term good or bad, but at least identifying its strengths and limitations? Resolution, everybody. That plays a big deal. Now, looking at the dimensions of a cell, it defines the cell size. And in general, if the cell is representing a larger area, that means that it's going to have lower resolution. Whereas if it is representing a smaller area, that means that it's going to have higher resolution in general. Now, there are other factors of consideration when it comes to, say, for instance, well, if this is a satellite, what kind of sensor does it have, so on and so forth. So, again, that was just a general rule they throw at you. And you're going to see that, well, looking at over to the far left here, we see this raster where things look kind of choppy and blocky, obviously. But the thing is, you can discern, it looks like a house and a driveway and a river. So, it's functional. Sometimes you don't have to have super crisp data in order for you to do analysis and make decisions. Now, everybody, this is considered grid data. If you open up the attribute table, you would see that, much like feature data, you would see a table that had fields in it that were describing each one of these cells and what the values are for them. So that's something you're used to. The interesting thing is this, is that when you look at the other side of the street, and that is something called floating raster data models, you're going to see that you cannot open up the attribute table. So let's talk a little bit more about that. Now, with floating rasters, the reason you can't open up the attribute table is because that the surface is being interpolated. And you start off with known values, and this example right here, you see in these frames that you have some kind of a surface and you have known values there, and you see that the system has been doing its thing to interpolate what other values are, and that's what you got here. You've got those different values, and it's using mathematics to figure out what it believes is the best estimate of what the values are as you move further away from those known points. So if you click on any one of these with your cursor and you're clicking away, what you're going to be getting back is a value that has values to the right of the decimal, 86.24 or whatever. And the reason it's doing that is because as you're moving your cursor around, you're clicking away, wherever you put your cursor down, it is quickly interpolating what it believes that value is, and that's why you can't open the attribute table, because in theory there's an infinite number of points. Like, for instance, if you're going to take a step, and how many points are there that you could find between your last position of your foot and your new position as you put your foot down. In theory, there's an infinite number of points that you could find along the way. So welcome to paradox, everybody. And so floating rasters are also a part of raster modeling. So using raster data, how do we solve spatial problems? Well, in Spatial Analyst, everybody, just like with feature data, there are some very common themes. Now, we're trying to represent a whole bunch of data on the landscape. So yes, just like with feature data, you're going to have data divided up into different layers of information. And just like layers, everybody, of course those layers are going to be common. Whatever the layer is, everything in that layer is going to be common data. Now, here's what's the really, really unique thing about doing raster analysis, everybody. With feature data, I'm sure you're familiar with overlay analysis, finding what objects, if I use the term rest upon each other, have the same geographic location, and then comparing them. Okay, I'm sure you have some familiarity with that. Now, picturing all those layers, what if for every one of those cells we assigned a value, a numerical value for whatever it is that you say, hey, by the way, I say, again, I'm using these non-scientific terms, sorry, like or dislike. Let's just say that if you have a high numerical value, there's something about that area that you say, something positive. Yes, when it comes to, the type of landscape or economic status of an area, that's good, or the bad is the one, whatever. Well, what you're going to see is that with Spatial Analyst, it will inherently, everybody, its inherent mathematical operation is addition. That's its inherent one. It doesn't mean you can't perform others, but what it's really doing is, in its simplest form of mathematics, is just simply finding all the cells that occupy the same space, all those different layers of raster data, and it adds up all those values. And you're going to see down in the lower right hand side, There's an example there where there's terminology like sand and dry, and okay, somebody's looking at maybe doing some kind of ecological study, and you're going to see that it was set up to where it is looking at the final result was set up for a true false or a Boolean sort of a response. And so there's other ways that you can work this, but that's it. I mean, really, at the core, a spatial analyst is taking different layers of rasters and looking at the values and then starting to, well, add them up. But you, of course, can do lots and lots of other mathematical modeling computations using spatial analyst. Now, if you're going to go down that route, there is something you have to note, and that is ranking. Now, ranking is when you identify a range of priority for every different layer of information. What you saw before, when you saw those cells that had 1 through 9 or whatever, well, what you're doing is this. When you do the ranking, you set up a uniform system throughout all the layers that you're going to be working with. If it was trying to figure out where you're going to put a new community, one of them might have been land cover, and you might have said, well, forest area is something I really am looking for. Okay, give that a high value. Areas that are water, okay, give that a very low value because I don't want to build in the water. I'm looking at areas that have that low cost of living. Okay, I'll give that a high value because that's of interest to me. So you play the game of identifying in your viewpoint, what do you believe that that layers values are worth? How should they be ranged? So something else that you do as you go through this process is doing this ranking of data. Okay, so now how do we proceed? You've got a lot of data and you need to solve a problem. For the conceptual model, everybody, step number 1, I know it looks really, really simplistic. You say, oh, no, what's the big deal? Stating the problem. Stating the problem is absolute. The reason being is this. If you cannot state the problem in one sentence, you've got to ask yourself why. And if you say, well, I want to build a community center in town, and also I want to make sure that the school system is also included into blah blah blah. And by now, of course, I'm trying to be creative, but you really make sure that that's stating the problem, that it's solid. You say, what am I doing? I am doing the following in the following geographic area. Don't worry, if you want to do another study, more power to you, but try to keep it straightforward and simple. Now, for the example of best site for a new school. Number 2, breaking down the problem. Now this is where you're going to start setting up the parameters. For every one of the parameters that you see of those 4 parameters, everybody, it's going to this. Now we're starting to set sail on the direction towards the kinds of analysis we're going to be needing to do, breaking it up in order to solve the problem. Near recreational facilities. Okay, looks like you're going to do some distance analysis away from existing schools. Distance analysis on relatively flat land. Okay, now we're going to start doing the ranging of land use. On suitable land, again, the same thing is going to start happening there. So now we're starting to get a feel for the kind of things we're going to be doing to solve the problem. And moving along in line with what was just shared, you're going to see that in this model right here, and by the way, mapping out your conceptual model is a big plus because you're going to be doing a lot of different things here. And here you start to see already that the operations, the general operations, are being identified, or the types of data, and so that is essential, because if you go into this blind and you say, well, okay, I kind of got an idea, and okay, let me do this, let me do that, you will be surprised, really surprised, in how quickly you can be confused when you're doing spatial analysis when you haven't mapped everything out. So please consider doing that. Now, step number 3, exploring the input data sets. you get the data that you are going to be needing for analysis, there is absolutely nothing wrong with exploring that data. I've seen quite a few of my students who, when they were working on projects, they wouldn't, well, maybe the right word isn't challenge the data, but at least review the data. Open it up. Again, you see here some examples here, graphing or whatnot, just to get an idea of what the data is like. Another thing that I share with my students too is even with feature data sets, when it comes to them doing attribute queries or whatever, I always ask them, I said, did you open up the attribute table? Did you take a look at the data beforehand? It definitely does help. You become more familiar with it, and you might find an inherent flaw with the data that you have. Now, number 4, performing the analysis, identifying and running tools that determine the model. This is where you finally plug it all in and you start to get some results. Now, step number 5, verifying the model result. You're going to look at what you have, and please note this isn't saying, well, I didn't get what I wanted. I think I'm going to go back in there and redo it until I get what I want. No, you're kind of going down a wrong road if you do that. But there's nothing wrong if you said, okay, looking at, say, the result, looking at the resolution of my final result, I say, hey, this is kind of difficult to work with. It isn't functional for me. And to go back in and change a few parameters and run it again. And I've done that. Many people have done that. It doesn't take too much to go back and change a few parameters. Now, number 6, implementing the result. What is it that you got? So now this is where being human is great, because we can see patterns and we make final judgments. Look at it and actually ask yourself, okay, what are we looking at? And quite often, this is a time where you could even bring in some additional sources of information. If you say, well, I looked at where potentially I wanted to build something, and well, I'm seeing that there's these areas up in the northwest area of my area that seem like they're very they have a very positive result. And well, maybe you could pull up some additional information or talk to people and say, okay, let's find out some more about this area. That's the fun part, because we bring in more of the human element into the analysis. Now, when it comes to final results, here you see a suitability map where you see high suitability, and then you all the way down to where it's down or up, or to where it's excluded and don't go there. And so you got this, and you say, well, that's really good. I seem to have kind of targeted the areas that I really like, but well, when it comes to the output, everybody, what if you were going to be presenting this to a committee or whatever, and they said, no, look, here, tell us yes, no. What places should we really be looking at? Okay, well, if you want to go down that road, let's do this. Take the data and say, look, here is suitable, here's unsuitable. And of course, this map doesn't have any other comparable data when it comes to location or anything, so sorry, it's kind of primitive. But still, you have an output where you're not changing anything. It's how you're presenting the data. That way, it's the most effective for you to make decisions. So everybody, when it comes to the conceptual model in general, please think it through. And along the way, it doesn't hurt to look at the data. When you get your, of course, definitely model it. Sketching things out is a good idea. And when you get a result, ask yourself, okay, is this functional? Do I need to change some parameters to make this more functional? And when it comes to the final output for the general public, you decide. You say, hey, by the way, let me simplify this, or maybe I have to make it more complex so that way people can, they have more to look at. I don't know. But well, that's the fun of being a GIS user. The human element introduced into the process.